In the last lecture, we studied the work energy theorem. In this lecture, we will start off with the amazing power of this theorem. It completely obviates kinematics. No need to use kinematics equation, and the solution becomes very, very simple and elegant. Then we'll move to another kind of energy called potential energy, and that is not due to motion. Kinetic was due to motion. Potential is due to position or due to configuration. Simply because you're standing somewhere, you have got a potential energy. And then we'll find that it is linked to a force which is a conservative force. The concept of potential energy is only associated with conservative force, not with non-conservative force. So we will understand both of these things, and then we will see the types of potential energy, especially gravitational potential energy. And then we will see that energy can be converted from one form to another, potential to kinetic and vice versa. When one energy increases, the other energy decreases and vice versa. That leads to conservation of energy at a broad scale. The energy of the universe is conserved. You can't create or destroy energy. But then we will also see one small corollary of this, which is conservation of mechanical energy, COME. And this lecture will point to COME that is covered in the next. Welcome to the portals of real learning. Enjoy your learning. Let us see the power of the work energy theorem. How elegant it is also and how easy it is. Find the speed of the body in these two cases when it hits the ground. First is an inclined plane which is smooth. What is the speed when it hits the ground? We can use kinematics because the acceleration is g sine theta down the plane. And why is that so? The weight is acting downwards. The normal reaction is acting normal. It has got no component perpendicular to it. And the component of mg down this direction is mg cos this angle. That is 90 minus theta. So the component of that is mg cos 90 minus theta or mg sine theta. Divide by mass, that is the acceleration. So what is the speed? Let us call this s. V square equal to 2as. Acceleration is constant, hence we can use this. U is 0. A is g sine theta. S is what? Sine theta is equal to h by s. So s is h upon sine theta cancels. V square is equal to 2gh and v is equal to root 2gh. Kinematics. But in this case, it is not a straight plane. The curvature is changing, so the angle of inclination is changing. Here the angle of inclination is this. Here it is lower. That is the theta which is varying continuously. So is the acceleration. And therefore we cannot use v square equal to u square plus 2as. But we can apply work energy theorem. Normal reaction is like this. In any small time interval, the displacement is perpendicular to the normal reaction. It does no work. Gravity is acting. And as you know, work done by gravity, when a body falls down, then only the vertical displacement matters. Work done by gravity is mgh. And the initial kinetic energy was 0. If the speed is v over here, then the final kinetic energy is half mv square. Change is final minus initial. Half mv square minus 0. That is a change. M cancels and we have the same answer. No need to apply kinematics. That's the power of work energy theorem. Another example. We don't even know the expression for the force, but we can find out the work done by it. Raindrop falls under the influence of gravity and an opposing resistive force by the air, which is upwards, gravity is downwards. This resistive force is known to be proportional to the speed of the drop. It is not constant but is otherwise unknown. Suppose a raindrop of mass 1 gram falls from a height of 1000 meters and hits the ground with a speed of 50 meters per second. What is the work done by gravitational force and the unknown resistive force? Gravity is very easy. It is going down. Then it is plus mgh, m in kg, g we are taking as 10. and the distance is 1000, that means 10 to the power 3 plus 10 joules. What is the work done by the resistive force? We don't even know the expression for the force. But applying work energy theorem, work done by all the forces is equal to the change in kinetic energy, which is again half mv square, half mv square. We get 1.25 joules. Work done by gravity is 10 joules, but the change in kinetic energy is much smaller. So from this equation, work done by the resistive force is 1.25 minus work done by gravity, which was 10, so we get minus 8.75. Obviously, it should be minus because the raindrop has a displacement downwards and the resistive force is acting upwards. Work done is negative. And see the beauty. We didn't have to know the magnitude of that force. Work energy theorem is very powerful and elegant, very simple to use. Now let me introduce you to another kind of energy called potential energy. Keep in mind that work energy theorem always applies. That is, work done by all the forces is equal to the change in kinetic energy. Suppose a body is taken from A to B via some curved path. What is the work done by gravity? We know that only the vertical displacement matters. Even though it doesn't fall here, it falls here. But the vertical displacement is h downwards, and the work done by gravity is plus mgh. And we can also do it in a more rigorous manner. Work done by gravity in a small dl1 displacement, then in dl2, then in dl3, etc. up till dln. So let's add up work done by gravity in each of those small displacements. mg dot dl1 plus mg dot dl2 plus so on up till mg dot dln, mg common, mg dot dl1 plus dl2 up till dln. Vector rule of addition is, if you have many vectors to be added, arrange them tail to head, 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 like that till the last tail to head. Join the initial point to the final point, that is the result. So dl1 plus dl2 up till dln is this vector L. So work done is mg dot L, which as you know is mg L cos theta, but L cos theta is equal to h, so mg h. If I took some other path, there wouldn't have been any difference. No matter what path is taken, the work done by gravity is the same. It depends only on the two endpoints, not on the path. And such forces are called conservative forces. Why they are called conservative, that is also having a lot of meaning. We'll see that. Another thing is, if I take the body back to A by some path doesn't matter, then you're back at the same point from where you started, work done is zero. So conservative force can be defined in two ways. One is that the work done by it is independent of the path, and the second, the work done by it in a closed loop is zero. Gravity is a conservative force. Spring force is a conservative force. Electrostatic force is a conservative force. But friction, air resistance, viscosity, they are non-conservative. The most interesting thing is that for any conservative force, there must exist a scalar function corresponding to that force. Let me explain. Since it is independent of the path, the work done is integral of f dot dr from some position A to some position B. The path is not important. Then I can assign a unique value of that scalar function at A and at B. And this turns out to be ub minus ua with a minus sign, and u is the potential energy. ub is the final value of the potential energy, ua is the initial. ub minus ua is the change with a minus sign, so this is equal to minus of the change in the potential energy, and this is the work done by gravity. Let me call it wc, conservative. With every conservative force, we can associate a scalar function corresponding to that force, and that unit is F dot dr means work or energy. And this energy we call potential energy. The work done by the conservative force results in a change in potential energy, and it is minus delta U. Now we can relate this as well as the work energy theorem. Very simple. Work done by conservative force by work energy theorem is the change in the kinetic energy. And now we are saying it is also equal to the negative of the change in potential energy. Now, if it were to fall straight from A to this point, then it would increase its kinetic energy. So this delta K would be positive. That means minus delta U is positive. That means delta U is negative. Delta U is negative. Change is negative. Final value minus initial value is negative. That means final value is less than the initial value, which means there is a loss in potential energy. So we can relate it this way, that a body has stored potential energy at any point. At A, it is higher than at B. As it comes down from A to B, its potential energy reduces and its kinetic energy increases. Whatever is the drop in potential energy is the gain in the kinetic energy. That is a result of all this. So when only conservative forces are doing work, then this will apply. That is, loss in one form of energy is equal to the gain in another form of energy, and vice versa. Potential energy concept is only for conservative forces. It is applicable only to those forces where the work done against that force gets stored as energy, doesn't get dissipated as heat or sound or something like that. See this example. I'm holding a cell phone at rest. I am exerting a force upwards equal to the weight, so it is at rest. Now I increase my force ever so slightly, just a little bit more than the weight, so that it starts to move up ever so slowly. The speed is negligible, but it is getting displaced. Finally, I'm able to raise it by a certain height. It didn't pick up any appreciable speed, so it didn't pick up any appreciable kinetic energy. But I did work. I did positive work. My force was upwards, displacement was upwards. So if I do work, then I lose that much energy. And I'm doing this work on the cell phone, so it should have gained. But I don't see any gain in kinetic energy. It has gained energy in another form, which is potential energy. And this energy is not getting dissipated. It is stored within the system. And the proof is, well, just release it. It will pick up kinetic energy at the expense of potential energy. You see, another reason why it is applicable only for conservative forces is this. If the work was dependent on the path, then I couldn't have assigned a unique value of the scalar function at the points A and B. It couldn't be unique. It depended on the path. But the whole logic, whole argument was that independent of the path, hence at A there is some value and at B there is some other value. That is why we cannot apply this for non-conservative forces like friction or air resistance or viscosity. The energy, potential energy, manifests itself when it is free to move. A falling body gains kinetic energy at the expense of potential energy. The use of the word conservative is not accidental. It has a deep meaning. Basically, law of conservation of mechanical energy. Mechanical energy is the sum of potential plus kinetic. Conservation of mechanical energy means that it doesn't change. It doesn't change when only conservative forces are doing any work. Other forces are either not present, or even if they are present, they are not doing any work. In such a case, mechanical energy will be constant. If there is any increase in potential energy, there will be a commensurate decrease in kinetic energy and vice versa. So the key point is this: work done by the conservative force is negative of the change in potential energy. Very important. Potential energy is an energy possessed by a body by virtue of its specific position in a conservative field. The example that we have been talking about is gravity. It is a conservative field. The concept of field is something else. Right now, you don't need to worry about it. Now, it could be due to position or it could be due to configuration as well. It is denoted by the symbol U. In mechanics, we have gravitational potential energy and elastic potential energy. Gravitational potential energy is simply due to the position relative to the center of the Earth, that is, height from the surface of the Earth. Farther a body is from the center of the Earth, larger is the potential energy. In other words, larger is the height from the ground, larger is the potential energy. It is by virtue of its position. Elastic potential energy is due to configuration. We know that when external forces act on a body, they can change the size and shape of a body. So once the shape is changed, then the body can regain its original size and shape if you remove the deforming force. And this is by virtue of internal restoring forces, which are called elastic forces. And this phenomenon is called elasticity. That is why we give the name elastic potential energy. It is the potential energy possessed by the body in the deformed state due to a change in its configuration. Take the bow and arrow, for example. You have the bow, you pull the string, you have to exert a force, and then you release the arrow takes off with a certain speed. Who gave this kinetic energy to the arrow? The string gave it. Now, the string, when it was not stretched, it would not be able to project an arrow. When it is stretched, when it is deformed, then the internal restoring forces are acting and there's a stored elastic potential energy inside it. The moment you release the arrow, that stored elastic potential energy converts into the kinetic energy of the arrow. Same thing with a rubber band and paper pellet. You might have done those kind of things as children. Or a spring mass system. You have a spring fixed at one end, you put a mass on the other end. When the spring is at its natural length, then there is no elastic potential energy because there is no deformation. You pull the mass, you have deformed the spring. And when you release it, it oscillates. So those are the two kinds of potential energies we come across in mechanics. Let's look at gravitational potential energy more closely. There's a body on the ground. I exert an external force just a little bit more than the weight, so it goes up to a certain height and then I stop. I'm still holding my hand over there. It has gone up to a height h. I did it very slowly, so it didn't pick up any kinetic energy. But I did positive work. The amount of work that I did is mg times h. My force was nearly equal to mg. It was upwards. H is also upwards. So I do positive work equal to mgh. This work that I do is stored inside the body as potential energy. Now, when you come to potential energy, we are only interested in the difference between one point and the other. And if there's a gain or a loss, there will be a commensurate loss or gain in kinetic energy. So which point you define as a zero level of potential energy is not important. But customarily, we say potential energy at the surface is zero. Then potential energy at a height h is higher than zero by an amount mgh. We have given an absolute value here, so we now have an absolute value here for the potential energy. The work done by the external agent got stored as potential energy, and the GPE, gravitational potential energy at the height h, is measured by the amount of work done by the external force in lifting it up against gravity. So U is equal to mgh at that height. If you increase the h, if you take it higher, the potential energy will be higher. And we know that if we release two stones from a tall building, one from the second floor, one from the 10th floor, when they hit the ground, the stone which was released from the 10th floor has got a greater speed. Why? Because it had a greater potential energy to start with, which converts to kinetic. Mass has gravitational potential energy in a gravitational field. See some cases, if you throw a body with some speed, then the speed u keeps on reducing and finally it stops at some point. The speed is reducing, the kinetic energy is reducing, but the height is increasing, so potential energy is increasing. Whatever is the increase in potential is the same as the decrease in kinetic. The gain in potential energy is equal to the loss in kinetic energy. If you drop a body from rest, then it picks up speed, so the V is increasing, kinetic energy is increasing, but the height is decreasing, potential energy is decreasing. Again, the decrease in this is equal to the increase in this. If you talk of a difference of height, h2 minus h1, if you take a body from here to here, then it gains gravitational potential energy equal to mg times this height through which it was moved, h2 minus h1. This much is h2, this much is h1. Reverse, there will be a loss in gravitational potential energy equal to mg times h2 minus h1. Conversion of potential to kinetic, lots of examples. You might have seen toy cars which are not powered by batteries. There is a key. You turn the key a few times and then release it, then the toy does something. A car can move forward or a toy can clap his hand. Basically, some motion is generated. In a watch, mechanical watches, there's a spring like this and you rotate the spring, it gets deformed, there is a stored elastic potential energy inside it, and then it converts to the motion of the hands of the watch as the spring unwinds and gains back its original shape and size. If you drop a body from a great height, then it picks up a large speed because the speed, as we saw, is equal to root 2 gh. And if h is high, the speed is high. Bow and arrow example we saw, spring example we saw. Some examples of conversion of potential energy into kinetic energy. Conservation of energy is a very important law of science. Energy can neither be created nor destroyed. It only changes form from one to the other. If we add all the various kinds of energy in the universe, the sum will remain constant of the whole universe. It may change form from one to the other, from kinetic to potential or vice versa, or for that matter, from light into electricity, or from heat into sound. All kinds of transformations are possible. But the sum total of energy in the universe stays constant. At a smaller scale, if I take an isolated system which has got no interaction with anyone, then for all the changes that are happening within the system, the total energy of the system will remain the same, and there's no work or energy exchange with the surroundings. A corollary of this is conservation of mechanical energy, which we frequently write as COME, conservation of mechanical energy. And this only happens when the work is being done only by conservative forces. In such a case, whenever there is an interchange between potential energy and kinetic energy, the total mechanical energy remains constant. Provided, of course, that there are no dissipative forces or non-conservative forces like friction or air resistance or viscosity. So I hope you found the concept of potential energy very interesting. We will continue this discussion on COME in the next session.